Good morning, ladies and gentlemen, and I'm very pleased to be speaking to you this morning about nitrogen and its interactions between soil and water. My name is Karl Richards, and I'm the head of the Environment, Soils and Land Use Department at Teagasc, Johnstown Castle. So before we get started, I'd like just to remind you of what you heard last week from Jenny Deacon in the EPA. And here you'll see on the right-hand side that Jenny or the EPA have highlighted areas that are at risk from nitrate. And it's specifically that risk increases as you move from northwest to southeast, as indicated by the darker colorations. In relation to those areas in the southeast, the EPA have noted that there's been an increasing trend in nitrate concentrations at the catchment level, as indicated with the yellow bar graph. As indicated here, and that a lot of those water bodies are in the south and east, and they have eutrophic estuaries, as indicated by the red areas, where nitrogen has been highlighted as a particular issue to do with water quality. So nitrate is a regional issue, and it increases from northwest to southeast. And this is primarily due to free draining catchments in these areas. So the soils are free draining, and therefore nitrate moves easily in those soils. And the reason for that is that nitrate isn't held in the soil, as it's a negatively charged ion, and it is therefore easily lost to water. Water quality trends are also going in the wrong direction, and this is really serious in that recent improvements up to 2012 were indicating agricultural intensification was being carried out that was compatible with water quality, but since then the indications are going in the wrong direction. So what contributes to nitrate loss to water? Well, I'd like to just take you through the different sources, the source pathway receptor model that is often used in water quality. And within that, what a source refers to in particular relation to nitrogen is sources of nitrogen. And that is fertilizer, manure, grazing, etc. So those are all sources of nitrogen. Those can occur in what we call point sources, as indicated on the diagram here, and those are indicated by leaking point sources such as slurry stores or oil tanks and things like that. You also have diffuse sources of pollution, which generally comes from larger areas such as grazed grasslands, where grazing returns by animals, nitrogen fertilizer, manure management can be potential sources of nitrogen. And then you talk also about non-point sources or non-agricultural point sources, which here is indicated by a septic tank coming from a house discharging higher levels of nitrate to the water. So how does the nitrogen get from the source to the receptor? The receptor is the river or stream or groundwater body. Well, there are different pathways for that, as indicated here. So this black arrow is indicating a groundwater pathway where the nitrogen and the water moves through the subsurface and then discharges into the river. This is generally the pathway for nitrate loss, and it is a slower pathway than overland flow, which is the next pathway, which moves across the land surface from an area of a nutrient source to a river. These are rapid transport pathways, and typically ammonium and phosphorus would be the nutrients at risk of movement by overland flow. But you can also get both pathways occurring, multiple nutrients being moved by each pathway. So it does start to get complicated. So as mentioned, the targets or the receptors are things like groundwater bodies, surface water bodies, wetlands, estuaries, and coastal waters, all of which are susceptible to nutrient input, where it results in excessive algal growth and eutrophication. So if we were to think of the perfect recipe for nitrate leaching, what would that comprise of? So in order to have nitrate leaching, you have to have nitrate in the soil, and you also have to have water percolating through the soil profile. Without either one of these, you will not have nitrate leaching. So you can have nitrate in the soil where there's no water percolating through that soil, it can't be transported and lost to water. And vice versa, if there's no nitrate in the soil, even if you have water moving through it, there's no nitrogen available to be leached. And the nitrogen cycle is somewhat complicated, and this is a simplification of it, and I'll guide you through some of the key elements of that. So us as farmers, what do? We apply nitrogen, and we apply that through fertilizer, manure, or it can be fixed via symbiotic nitrogen fixation by legumes such as clover. And why do we do that? We do that to increase the inorganic pools of ammonium and nitrate in the soil. And these are the forms of nitrogen that are available for plants to uptake. And plants can uptake both ammonium and nitrate, not just nitrate. So why is nitrate a problem? Well, as I outlined previously, nitrate, which is one of the mineral forms of nitrogen in the soil, once it's in the nitrate form, it is susceptible, or it can be lost to groundwater via leaching, where water percolates through it. It's also subject to microbial processes called denitrification, which reduces the nitrate to nitrous oxide and N2 gas. Nitrous oxide is a potent greenhouse gas, and N2 nitrogen gas comprises 78% of the air that you breathe. So it's in our interest to try and minimize the nitrate pool in the soil, to try and minimize our losses of nitrogen to the environment. So how much nitrogen is acceptable? These are levels that I received from the EPA when I asked them what's acceptable. So in order to protect freshwater ecology, you need to keep the concentration below 1.8 milligrams per litre of nitrate nitrogen. For ammonium, the concentration is an awful lot lower, and that's because ammonium can be very toxic to aquatic life forms, and the phosphorus is even lower again. To protect our estuaries and coasts, the maximum concentration is 2.8 milligrams per litre of nitrogen, and that's either nitrate or ammonium, or the two together. And that is the concentration at which the salinity of the water is zero. So this is the last fresh water sample before it starts to get into the estuary. So that's a very low concentration. Traditionally, water quality has been related to the drinking water limit, and there the EPA uses a mean concentration of 8.5 milligrams per litre, expressed as nitrate nitrogen. But you also need to be aware, sometimes people talk about nitrate on its own, and the limit for nitrate is 37.5 milligrams per litre of nitrate. So the 8.5 is equivalent to 37.5. So it's very important that you understand what form of nitrate you're referring to. In this presentation, I'm referring to nitrate nitrogen. The maximum concentration in drinking water is 11.3 milligrams per litre, or 50 milligrams per litre as nitrate. That means if you get one sample above 11.3, you are in breach of the Drinking Water Directive, and you have supplied drinking water that is not fit for human consumption. So that is a maximum concentration. It's not a mean concentration. So what factors influence nitrate in the soil? Well, the application rate of fertilizer, or the amount of nitrogen that you put onto the soil, is important. The timing of when you put that on is really important. The soil nutrient status, the crop type, and the overwinter cover that you have are really important. I'm going to guide you through each of those now. So in terms of fertilizer application rate, what we find, this is some old research, but it's still very valid. This would be the uptake or grain yield on the y-axis, and applied nitrogen on the x-axis. And this indicates that as you increase nitrogen fertilizer, your yields increase. The red line, as indicated here, shows that as you increase nitrogen fertilizer rate at about 160 kilograms per hectare of fertilizer, you start to see an increase in the amount of nitrogen that's in the soil that's available to be leached. And there becomes an optimum there at which you get your maximum yield with the minimum amount of nitrogen in the soil available to be lost. And that's referred to as the N optimum. So as you increase above the N optimum, you preferentially increase the amount of nitrogen that's going to be lost to the environment than what's going to go into your crop. And ultimately, a farmer is interested about maximizing their yields and minimizing their environmental impact. If we talk about a grass crop, there are two lines here. The green line indicates the grass requirement for nitrogen in kilograms per hectare per day, and the red line indicates the amount of nitrogen that is released from the soil through a process called mineralization. And depending on your soil type, soil nitrogen mineralization accounts for somewhere between 50 and 150 kilograms of N per hectare. And typically a grass requirement for nitrogen is somewhere around the 400 to 500 kilograms per hectare. The difference between what the soil releases and what the grass requires is referred to as our fertilizer nitrogen requirement. And this is where we provide farmers with fertilizer advice to make up the difference between what's released from the soil and what the grass requires. There are periods of time where, particularly in the early spring and in the later in the autumn, where soil nitrogen release exceeds the plant's requirement for nitrogen. And this, I suppose, is the foundation behind calendar farming and why there are limitations put on when you can apply chemical fertilizer and also slurry to your soils, because you should only be applying nutrients to a crop that requires that nutrient. Otherwise, it's waste disposal. And there are variations between years, there are variations between soils, but by and large, this pattern is similar across the country. And so the effect of grazing on nitrate leaching. So why do we get nitrate leaching? And that's generally because more nitrogen is applied to the soil than the crop can uptake. And within our grazing pastures, urine patches are the dominant source of nitrate that is lost to water. And the reason for that is that they contain high nitrogen loadings. They've been reported up to 1,000 kilograms of nitrogen per hectare equivalent in a urine patch. In Ireland, we estimate the loads are more likely in the 300 to 500 kilograms of nitrogen per hectare. But that is a large amount of nitrogen applied in a very small area. And grass can uptake that nitrogen, but it depends on the time of year of which it is deposited. So at certain times of the year, there is limits on how much can be uptaken. Urinations in autumn can increase the risk of nitrate leaching, and that's because you're combining water movement in the soil with reducing grass requirement for nitrogen, and you're applying a high load of nitrogen. So measures to reduce nitrogen losses stem around either influencing the concentration of nitrogen in the urine, and you can do that through dietary manipulation and reducing nitrogen in the diet, in concentrates, etc., or basically controlling the number of urine patches in a hectare or in a field. And that can be done by manipulating stocking rate or manipulating the duration of which cows are in a field. Further research that we've done has looked at changing the timing, but also using nitrification inhibitors, which reduce the buildup of nitrate in soil. So in terms of some of our own research here, we've looked at leaching from 3 different soil types. Those soils are a Wexford Rathangan soil, which is a poorly drained soil, Limerick Elton soil, which is a medium to well-drained soil, and then a soil from Clonakilty, which is a well-drained soil. And what we can see is when we only look at fertilizer, the amount of nitrate that gets leached is generally low. And there wasn't much difference between soil types in how much nitrogen was leached from just fertilizer applications over a grazing year. As we start to then look at urine patches deposited during the spring and the summer period, which also received fertilizer, you can see that there wasn't a significant difference in the leaching from spring and summer applied urine. But as we move into the autumn, you can see the amount of nitrogen leaching that comes from urine patches increases as we move from September into November. And we can also see a very significant effect of soil type, where the amount of nitrate leached from the most well-drained soil was significantly higher than the other soil types. So this is, again, a clear indication of nitrogen in excess of plant requirements being deposited on the soil. In terms of, is there a relationship between stocking rate and nitrate leaching? Further research that we published from Grange under an intensive beef system with Michael Drennan indicated that the blue line shows the mean nitrate concentrations over 3 different years on what we call an intensive conventional system, which was stocked at 210 kilograms per hectare of organic N, so a derogation level beef farm, versus a reps beef farm which was stocked at 2 livestock units or 170 kilograms of organic N per hectare and was receiving, I think it was 80 or 85 kilograms of nitrogen fertilizer, compared to the 210 kilogram of organic N, which received I think it was about 200 kilograms of fertilizer nitrogen. So what we can see is there was significantly lower nitrate leaching on the reps grazing system than the very intensive grazing system. And we can also see that there was significant between year differences as well. In year 1, the losses between the 2 systems were not significantly different, but the differences appeared in years 2 and years 3. And that's quite often seen in nitrate leaching studies, is this interannual variation. And I'll touch on that later in the presentation. This is some work from Curtin's farm, one of the Moore Park farms, published a number of years ago, where they investigated 3 different stocking rates of 210, 250 and 280 kilograms of organic N per hectare. And they looked at nitrate leaching at 1 meter below ground level. So this isn't nitrate in groundwater, this is nitrate in the soil that's still being moved or still percolating towards groundwater. And on average, what they found is the concentrations were significantly higher than the drinking water standard and higher than the environmental standards that I mentioned earlier. But they also found that there wasn't a significant relationship between the stocking rate and the rate of nitrate leaching either. Crop type and soil type all have an effect on nitrate leaching, and in particular on, I suppose, how much nitrogen ends up going into the crop. Grassland typically has a longer growing season than most crops, and therefore generally has a higher rates of nitrogen uptake and a longer duration of nitrogen uptake. When we look at some of our cropping systems, spring cropping systems have a very short, confined growing period between spring and harvest in August or early September. So they have a very short period of time to uptake their nutrients, and winter crops have an ability to uptake nitrogen from the autumn through the winter into the spring as well. So they have a longer period of nitrogen uptake. So when we looked at in terms of our nitrogen dynamics in the cropping system, particularly a spring system like this, the top graph here shows nitrogen uptake between when we sow the crop and when we harvest it. And then when we look at the nitrogen released from the soil, we can see that there's a period of time where there's no crop growing and there's still nitrogen being released from the soil, and there's still nitrogen in the soil after the crop as well. And where there's nothing growing on that soil, that nitrogen is available to be lost to groundwater and impact on water quality. And one way of addressing that is by ensuring that you have something growing over the winter. And this is really important from a carbon perspective, a water quality perspective, and soil fertility perspective, in that you're capturing nutrients and organic matter and reintroducing that into the soil. Here's an example of a mustard cover crop that we were investigating in Teagasc Park in a long-term study there with Richie Hackett. The results of that study I'm showing in the next graph that's been published in a number of papers. So what we see here is on the y-axis, we have the average soil solution nitrate concentration. So that's at 1 meter below ground level. So it's not in the groundwater, it's in the soil, still percolating towards groundwater. And the y-axis, we see the different years of our study. So this was carried out over a 6-year period. We had a number of treatments. The green line, we'll start with the blue line. The blue line indicates a standard spring barley system, where either the solid line shows where we had sort of reduced tillage, or the dotted line is where we had conventional ploughing. And what you'll see there is there was no significant effect of of reduced tillage versus ploughing on nitrate leaching. But when we introduce a cover crop, which are the green lines, we can see that we dramatically reduce the concentrations of nitrate in the soil solution over the winter period. And that's significant because it reduces how much nitrogen is actually being lost to the environment. But one of the big things we took from this as well is that there's a huge inter-year variation. So this study was carried over 6 years. It had spring barley grown every year. It had the same level of nitrogen fertilizer applied every year. The only things that differed were the weather conditions. And those weather conditions can impact the growth of the spring barley, but more importantly, they influence when leaching occurs and how much water percolates through the soil. We followed that up with a little bit more investigation. And this graph here is a little bit complicated, and apologies for that. On the y-axis, we have our predicted soil solution concentration. So this is where we've developed a model, and that model used rainfall and soil moisture deficit as the main factors in the model. And this model explained about 60 to 70% of the variation in our nitrate data. So based on knowing the rainfall amount, so as rainfall increased or decreased and soil moisture decreased, we got soil moisture deficit increased and rainfall decreased, we got a significant increase in nitrate concentrations in the soil solution. And this is independent of anything that a farmer can do. So weather has a huge impact on concentrations and of loads being lost from the soil. Now, if we move away from the sources of nitrogen to the pathway factors, so this is the factors that affect the movement of that nitrate. I've already started to outline the importance of rainfall, and that's both the quantity and the distribution of the rainfall over a year. Effective rainfall, and so what I mean by effective rainfall, that is the amount of rainfall minus the amount of evapotranspiration. So typically in Ireland, we have between 500 and 600 millimeters of evapotranspiration, which is moisture returned to the air by the growing plants. And if our average rainfall is somewhere around 1100 millimeters of rain, therefore we've got somewhere around 500 to 600 millimeters of effective rainfall. And that basically dilutes and transports the nitrate through the soil. Soil type is also important because it controls the amount of oxygen in the soil, and that has an effect on how much denitrification or how much of that nitrate can be reduced to gaseous forms. The depth of the soil and subsoil are really important because that determines how quickly the nitrate can be lost to water, and it also influences the oxygen status in the subsurface as well. So this is a typical water balance model for Johnstown Castle, and you can see here on the y-axis we have monthly rainfall and evapotranspiration in millimeters per month, and on the x-axis we have the month of the year. And what we see in January is typically evapotranspiration, which is the dotted line, is generally low, because grass growth is generally low, and rainfall is high. So the difference between the two is how much effective rainfall there is, as indicated by the shaded high-risk area. So you can see generally that is a high-risk time period because you have water moving through the soil and you have not a huge amount of plant growth at that time period. As we move into April and into May, typically evapotranspiration exceeds rainfall, which means the soil starts to dry out. And that's what we term soil moisture deficit, and that builds typically over the summer period until a time point at which evapotranspiration decreases below rainfall. And typically that happens somewhere between sort of August and November, depending on the particular time of the year. And then as we move into the autumn, before water can typically move in a soil, you have to return the soil to field capacity, which means that soil moisture deficit needs to be filled with the incoming rainfall. And that's indicated here from September onwards, where you see rainfall is higher than evapotranspiration, but there's a white period of time which is not indicated as high risk. And the reason for that is the soil is still wetting up and you don't have moisture actively moving through the soil. So that's on average, but every year is different. If we look back to 2012, where we had leaching events occurring during the summer, we had animals in yards because of very poor summer weather conditions. And then we look at 2018, where the soil moisture deficit continued well into the autumn period. So there's definitely both regional and interannual variation that we see in this, in relation to soil moisture deficit. We did a little bit of work then using some long-term trends that we published in the paper Schulte et al. Back in 2006. And within this, we plotted the monthly effective rainfall. So this is the amount of water that can move through the soil. There's two of the synoptic stations here, Belmullet and Kilkenny. And what you'll see in Belmullet, you know, typically every month of the year there was some moisture moving through the soil. Up to 100 millimeters in some months, and then reducing down in the summer period. Whereas in contrast in Kilkenny, you can see as you got to month 6, so June, month 7, July, you had very, you know, there typically wasn't any moisture moving through the soil. And that's because soil moisture deficits built up. And that has an impact, because where you have moisture moving through a soil, it transports nutrients with it, where they're available to be lost in the soil. So you can see in Belmullet, the pathway occurs a lot more often, and the pathway is occurring to a larger extent than in Kilkenny. You also see that if you take the total volume of effective rainfall in Belmullet, and I don't know off the top of my head here, but I'm guessing it's somewhere maybe 700-800 millimeters, and compared that to Kilkenny, which is probably more likely 200-250 millimeters of effective rainfall. This has a huge effect on the concentration of nitrate that gets leached, because you take a given mass of nitrogen to be leached, say 50 kilograms, you dilute that either in 700 or 800 millimeters of rainfall or 200 millimeters of rainfall. It's going to have a fourfold effect on the concentrations that you see, and I highlight that in the next graph. So on the y-axis we have the mean concentration if 50 kilograms of nitrogen per hectare were leached. So if a whole bag of fertilizer per hectare was leached out of the soil, and these would be the relevant concentrations that you would potentially observe. Where on the x-axis we have effective rainfall, which changes from 250 millimeters, which would be typical in the southeast, to 500 millimeters, which would be more sort of the Cork region, and then increasing to 750 and 1,000 millimeters, which would be more like in the west of Ireland. And what you can see on that line is there's a dramatic reduction in the concentration, the predicted concentration, as you increase effective rainfall. So this also influences the concentrations that are seen in the environment. And as I mentioned, in the southeast, as indicated in the previous slide, conditions are a lot drier. So in terms of soil type is important. Reason for this a lot of the time is due to water holding capacity. And I know I'm running out of time now. Here's a couple of typical soil profiles you might see in the country. You've heard these two soils already, Rathangan, the poorly drained Wexford soil. You can see there's grey mottling in it, indicating areas of anaerobic zones due to water reducing conditions, reducing the iron from its oxic state to its reduced state, which is the grey colour. And then you've got a really nice free draining soil from Clonakilty, as you can see from those deep brown colours all the way down the profile. Why is water holding capacity so important? On the y-axis here we have the depth that nitrate could leach, and we have 3 different soil types. For a given level of effective rainfall, here it's 100 millimeters, on a sandy soil we predict that that would leach to 450 millimeters, or nearly half a metre below ground level. On a loam soil that would be 300 millimeters, and on a heavy clay soil that would be more like 200 millimeters below the ground. So for a given level of rainfall, you can have nitrate pushed through the soil to different depths depending on the soil type that you have. And that's really important, because the speed of that movement influences the ability of the crop to uptake the nitrogen, but also influences the process of denitrification. So the longer the nitrate or the nitrogen is in the soil, the more likely it is to be reduced to nitrogen gas. Water table is also important. Shallow water tables would typically have runoff and denitrification because they would be typically wet soils, whereas deeper water tables have longer travel times, and there is some potential for attenuation. Where we insert artificial drainage into soils, we speed up the delivery of water to surface waters, and that can result in increases in nitrate and ammonium and phosphorus in those surface waters. And wet soils with high water tables can be easily identified, with grey mottling, etc. And most farmers will know those anyway. I'm going to skip these and get to my final couple of slides. The Agricultural Catchments Programme has been running since 2008, 2009, and over the 10 years of monitoring so far, this is, I suppose, the summary of what it's been finding. And if we look at the nitrate nitrogen, which is the middle bar below the photographs of each of the catchments, you'll see an indication of what the mean concentration over that period was. And you can see in the northwest and the north that typically the concentrations were below 2 milligrams per litre, so good from an environmental perspective. And as we move down into Louth on the east coast, the northeast, you can see the nitrates are quite high. And again, that's an arable catchment. And again, that's where you have land use effects impacting on nitrogen availability. And as we move down the east coast into Wexford, you can see that there are two catchments. One is a poorly drained catchment, and the nitrate concentrations are below 2.5 milligrams per litre. And then we have an arable catchment, and the nitrate concentrations are just below 7 milligrams per litre. So again, indicating both the effect of land use and the effect of soil type. And then as we move west to Timoleague, we can see that the nitrate levels there are closer to 5.5 to 6 milligrams per litre. And again, from an environmental perspective, the levels in the south and southeast are breaching what the ecological standards are. And that reflects both changes in management practices and land use and the intensity of those and the soil types. And that directly relates back to the initial slide from the EPA indicating areas at risk from nitrate leaching. So to summarize, Mark, in terms of the source pressure, we need to balance nutrient supply to crop demand. And as I said, David Wall will go into that in a lot more detail on the 26th of June. We need to avoid autumn and winter applications, or applications where rainfall is greater than evapotranspiration. So we need to be careful when water is moving through the soil. In terms of, little and often type approach can help to reduce the amount of nitrogen or nitrate that gets leached. I'm going to skip. So there are other sources of nutrients on farms, and particularly dirty water or soiled water is one to be careful with, because there you're applying water and nitrogen at the same time. So when you over apply that, it can result in nitrate leaching directly. Ploughing of grassland or any events like that, where you do that event in the springtime, you get lower nitrogen losses than when you do it in the autumn time. And again, that relates to the pathway being in operation in the autumn time and less so in the springtime. And in cropping systems, particularly spring cropping systems, overwinter cover is particularly important to reduce nitrate leaching. In terms of the pathway, then, timing of leaching varies nationally, and I would say it varies within catchments as well, based on both the localized hydrology and the soil conditions. Anaerobic or wet conditions lead to denitrification and reduced nitrate leaching, but result in greenhouse gas emissions. And where we have soils with low water holding capacities, this increases the depth to which nitrate can be leached in the soil. So again, these are soils that we need to be careful on in terms of, I suppose, applying nitrogen relating to the timings of when pathway occurs. And catchment hydrology, the overarching findings from the Agricultural Catchments Programme is catchment hydrology is king in terms of soil type and influencing how much nitrate can be leached within those catchments. So That's me, Mark. Happy to take some questions. I think there's probably some there.
That's great, Karl. Thank you so much for that. That was a lot of information in a short period of time. I think a few of our viewers were a little overwhelmed with some of the graphs that you presented, but I know, look, today is about really, I suppose, scene setting for the following conversations that we're going to have with Karen next week and with David then the following weeks as well. Karl, I mean, you talked about the complexity of the nitrogen cycle and I suppose the complexity associated then with soil moisture deficits, you know, on the ground for farmers making decisions around nitrogen application. You know, are there any decision support tools or rules of thumb there when it comes to actually identifying safe periods for spreading or indeed grazing?
Yeah, so, you know, I think there was a recognition a couple of years ago in the 2018 drought that we really needed to improve our communication to farmers and to bear in mind the reduced requirements of grass growth. So there is a working group in Teagasc that is dealing with soil moisture deficit and how much nitrogen should be applied and when it should be applied. And a lot of that advice is being communicated through Grass 10 at the moment with our colleagues in Moore Park who are running pasture base. And it is an active area, and I think it's an area that we need some decision support tools. You know, the fertilizer planner within nutrient management planning online will help, but that won't, I suppose, tailor it towards regional and field to field variations, because every farm is going to have a wet field where the grass is probably still hopping out of the ground, and they're going to have a very dry field where it's barely growing. So, you know, measuring grass, measuring what's happening on their farm is really important for farmers, and then to tailor their management practices to what they see is really important. And I suppose the bottom line of what we're trying to get across is think about what you're doing. If the grass isn't growing, it doesn't need nitrogen, and if there is nitrogen in the soil already, it's not going anywhere. It's still there, and it'll be there when the rainfall hits. And even when the rainfall hits, it's like that pool is likely to increase through soil mineralization. So you may not require the full nitrogen requirement after that re-wetting event.
Karl, I'm going to ask you a maybe more challenging question. You're responsible for the research in relation to water quality, but also climate change. You mentioned a couple of measures there in relation to avoiding riskier periods at the end of the year. And you also mentioned, I can't recall now what the other measure, but there are some measures within the climate, the marginal abatement cost curve, such as extended grazing, that would suggest, some people would say, well, is there a potential conflict there, or how are we managing that potential issue of pollution swapping, as we sometimes call it?
Yeah, so it is, as you get into autumn grazing, there's a number of factors happening. So typically when we graze in the autumn, our ammonia emissions are reduced dramatically compared to when animals are in a farmyard. So the first thing is we're reducing ammonia emissions by extending the grazing season. And we're also reducing the amount of, I suppose, purchased feed that is required. Also, as we move into the autumn, stocking rates typically reduce. So even if you have a high rate of leaching from a single urine patch, if you have fewer urine patches in the field, that will reduce the overall leaching. So there are grazing management practices that I suppose help to mitigate some of the effects that you might see. We've done a lot of work in the past on things like nitrification inhibitors, and we know they work. They dramatically reduce both leaching and greenhouse gases, but at the moment they're not acceptable from a public perspective or from a cost perspective, but they're incredibly effective. And there's probably more work we can do in terms of animal dietary manipulation at that time, in terms of trying to reduce nitrogen intake, because we know also as we reduce nitrogen intake, the amount of nitrogen excretion reduces as well. So there's quite a number of interacting things that can be done at that time of the year. We
have lots of excellent questions coming through here, and today we have nearly 400 people watching us today, so it's it's great to have so many people joining us today. Pat, do you want to kick off some of the questions?
Yeah, no, there's a few, and I think there's been quite a few questions about that autumn management issue. There's one there as well about ploughing in the autumn and whether or not that's something that should be advised against at this point.
So some of the research we would have observed in the past is again, it all depends on the growing conditions after you reseed your pasture. If you've good growing conditions afterwards, it will uptake the nitrogen that you release from ploughing. If you've poor growing conditions after ploughing, whether that's in the autumn or the spring, you're going to have higher losses. The advice would be to do that ploughing event in the spring rather than the autumn, because you're giving a much better chance for your pasture to establish. But that has practical implications for a farmer on managing his grass availability as well. So there's a lot of interacting factors there.
Yeah, and another question there, it's saying there appears to be a balance between nitrogen emissions and leaching losses. Where does protected urea fit in this scenario?
Okay, it's a good question. So what we observe when we look at the soil nitrogen pools, that ammonium and nitrate pool in the soil, under protected urea, we see that the nitrate pool is very stable and is low, compared to when we look at calcium ammonium nitrate, the nitrate pool in the soil is much higher and it's very episodic, or it changes rapidly in relation to fertilizer events. So you would predict that nitrate leaching from protected urea should be lower. We did a grazing study on that, and we didn't find any significant difference in the levels of leaching between both. And the reason for that is it was a grazing study, and the variability that you observe is quite high. But from a soil pool perspective, there's less nitrate in the soil pool, and that's why you get lower nitrous oxide emissions, and therefore you should get lower nitrate leaching as well.
Okay, a question there in terms of the cover crops. What's your view of cover crops being grazed by animals across the winter?
Again, there's a balance there of, I suppose, between the urine patches going back on and how much nitrate could be leached from them. It depends on the soil type, and it depends on how much rainfall there is. So in some areas, it's probably perfectly fine and isn't having an impact. It's not something that we've looked at. So I'm sort of talking a bit hypothetically. And it's going to depend on exactly how many, urine patches, etc. there are. If you wanted to reduce the losses, you could cut it and bring it into the yard for the animals, but that increases expense. So I'd say on drier soils, you're going to potentially increase nitrate leaching, but it is something that needs more research.
And a question here is, has there been any work done on the effect of diet and urine content?
There has, and again, colleagues in Moore Park have a model there which relates animal diet with N excretion. And we can see it from the likes of pigs as well. As we reduce the amino acids in the diet, the amount of nitrate that gets excreted decreases, and that's one of the measures in the MAC as well. And one of the measures in the MAC as well is reducing crude protein in concentrated feeds, and the effect of that is reducing N excretion. And again, we do have very strong science relating the concentration of urine to both nitrous oxide and nitrate leaching. So it is something that we'll be able to model in the future.
Karl, we have a question here in relation to, we know that there's regulations around slurry spreading and farmyard manure spreading during the autumn period or winter period. Question here is that, should the turning out of livestock be regulated, given the figures that you've mentioned there?
Again, I wouldn't get caught. The figures I'm talking about are a urine patch. The urine patch scale. They're not at a field scale or a catchment scale. So I don't think that, you know, what we are promoting is extended grazing. And, you know, there are other tools that you can use instead of twice a day grazing, or instead, you know, you can reduce the period of which the animal is at pasture. So where there's twice a day milking, you know, research from Moore Park would indicate that the animals can ingest a lot of their feed during the period between morning and afternoon grazing. So if they're only out for a period of 5 or 6 hours, it reduces, you know, the number of urine patches by 75%. You basically, it's directly related to the time of pasture. So there are grazing management practices that could be carried out and are carried out that will reduce the number of urine patches. And as I also said, stocking rates typically reduce as you move into the autumn as well. So they, you know, they might graze one paddock and they might not graze that paddock again until springtime. So it's not that simple.
A good number of questions coming in about January and February in terms of nitrogen application and advice in relation to it.
Yeah, so again, I know David's going to go into that in a lot of detail. I just go back to what I said before. It all depends on your crop growth. If the crop is on a dry soil in that period of February and March, or late January, February and March, if it's on a dry soil, the temperature conditions are right, the moisture conditions are right, and the crop is growing, then it requires nutrients. If the soil is wet and cold and the grass isn't growing, it doesn't require nutrients. So again, it's down to farmers walking their farms. They'll know the fields that get early grass, they'll know the fields that do not, and it's to tailor their practices accordingly. At that time of the year, using your manure is a really good idea. There is obviously a lot of nitrogen in it, and you will reduce your ammonia emissions at that time of the year as well. So again, it's around judicious precision management around fertilizers at those riskier times of the year, be it the spring, or this can happen in a wet summer. We remember back to 2012 when we were feeding silage in the middle of the summer and animals were brought in. So, like, you know, farmers do recognize when their fields are being impacted unduly by weather, and they usually adapt their management practices accordingly.
Karl, we have a question here relating to, I suppose, the future of weather patterns in Ireland. Climate change models are suggesting increased rainfall in the winter, more intense rainfall periods, and more droughts during the summer. And you know, so we've substantial variations across the country in soil type and weather conditions. So the question here is, do we have an estimate of land area where intensive production is possible, or do we need more specific advice related to land carrying capacity rather than general messages? I suppose this does come back to the age-old question of land use planning, which is a controversial area.
Yeah, and like I would argue as well, like you've got parts of the west of Ireland where the soils are free draining and have a good carrying capacity. So it's not just regional differences, it's within farm. You know, you field, as I said, there's the dry field and there's the wet field, and the farmers do know where those are. I think we do need to address climate adaptation further, and it's something that we are looking to some extent in Johnstown Castle with the inclusion of multi-species swards, where we have deeper rooting species to help us, particularly in drought conditions, avail of moisture deeper in the soil profile. And we have a dairy systems experiment underway there in Johnstown Castle, and there's a reciprocal one on Curtin's farm as well. So we're able to look at the effect of that across two different soil types. And both of those systems are at significantly reduced nitrogen levels. They've reduced by, I think, 100 to 150 kilograms per hectare. So the N rates being applied are somewhere between 100 and 150 kilograms per hectare. Running a high sort of stocking rate dairy system on.
Okay, thanks for that, Karl.
Kind of an interesting question, kind of indicating our efficiency of use of nitrogen at being about 25%, but how much of the remainder of the nitrogen is in an environmental, or is lost in an environmentally damaging way?
That is a really difficult question to answer because it is soil type specific. Recent research that we published in one of the Nature journals We identified a new pathway where nitrogen is reduced to N2 without nitrous oxide. So this is a process called co-denitrification. That was the dominant nitrogen loss pathway, and it resulted in N2 going back to the air. So when you look at those excesses, you're building up nitrogen in your organic matter pool every year. I mentioned there's a release of between 50 and 150 kilograms per hectare in mineralization, but there's going to be a reciprocal immobilization of nitrogen as well, and it could be even greater than that. So the two big unknowns around nitrogen surpluses are how much nitrogen went off as N2 gas and how much nitrogen got immobilized back into the soil organic matter pool, which is increasing. So it is, can't give a simple answer to that, and it is going to relate to soil type. And that work has been shown in the Netherlands as well, where you can't just take simply a nitrogen surplus and predict groundwater nitrate concentrations from that. It just doesn't work.
Okay, a couple of questions in relation to multi-species swards, and I suppose it's recognised that because of deep rooting, they have an impact in terms of drought resistance. But there's I suppose a corollary question is, does that have an impact in terms of taking up nitrogen maybe from a lower level within the soil and reducing nitrate losses as a result of that?
Exactly. So, most of our perennial ryegrass swards have rooting depths. If you just look at the main roots are in the top 20 centimeters. There might be roots below that, but it's typically pretty shallow. So once water's gone past that depth and there's nitrate in it, the plants can't access it. So if you have a deeper rooting species such as plantain or chicory, or deeper rooting grass species, then they are able to access both nitrogen and moisture deeper in the soil profile, but other minerals as well, phosphorus and other, I suppose, micronutrients too. So they could potentially reduce leaching as well as greenhouse gases and enhance carbon sequestration. And there's one other aspect in terms of plantain. So Plantago, it has been linked to increasing biological nitrification inhibition. So what that means is people, particularly in New Zealand, have observed lower amounts of nitrate leaching coming from swards that have plantain in it. And that's because it affects the microbial community in the soil to reduce the bacteria that basically oxidize ammonium to nitrate.
A question here, is there a case for reviewing advice on maximum nitrogen rate in any given application split to reduce the risk of leaching, especially given the more volatile nature of rainfall patterns?
Absolutely. So if we go back to that grass growth requirements, that's what our I suppose monthly fertilizer plan has done in the past and continues to do, and that's been further refined now with Pasture Base Ireland, where we can look at the current grass growth and the predicted grass growth conditions over the next 10 days. So we are actively doing that in Teagasc at the moment and providing that advice to our clients through Grass 10 and Pasture Base Ireland.
We have a question here in relation to the ASSEP program, and maybe Pat, you might want to come in on this as well. I know it's early days yet, but are there any insights onto what was making a big difference in those catchments to reduce nitrate leaching, and any practices that farmers struggled to implement in ASSEP? But maybe I suppose that question could also be extended to the catchments program. Any comments on that?
So look, I suppose the overarching comment would be the more engagement a farmer has with an advisor, the more likely they are to modify decisions that they're going to make. So where they've got good advice, it's coming to them in a timely manner. It gives them the ability to make decisions. And I suppose a lot of the time farmers, they're time starved. Time isn't something that they have. So when somebody can really help them quickly to make decisions, then it has a very positive effect. And also just the pure raising of awareness around particular issues puts that more in a farmer's mind in terms of when they are going out to, say, spread manure, for example, or spread fertilizer. So I think I'm not sure, and I haven't seen the exact improvement results from MASSAP. I know Jenny mentioned it briefly last week, but I would expect, alongside with the agricultural catchments program, it's about co-generation of ideas with the farmers. So farmers know their systems and their farms the best, and working with a professional to modify what they're doing or to enhance aspects of things that are going well already has real dividends. And then sharing those experiences across with other farmers in their catchment is really important.
Pat, do you have any comment on that?
Yeah, I think one of the things, and it's really what today's webinar is all about, is trying to improve the understanding of the situations where there's risk of loss. And I think that's what really Karl has outlined for us today, that there are periods of the year that there's significant loss, and practices at those times of the year on farms are absolutely key to reducing. And that's been the message, I think, that advisors have been bringing to farmers in terms of trying to reduce losses to water in those nitrogen sensitive areas. And I think today is I suppose a ramping up of that to try and get all professionals working with farmers, all advisors working with farmers, to have a full understanding of those risky periods and how that should impact on fertilizer and I suppose organic fertilizer advice.
Yeah, so look, I suppose there's some questions about the level of which the presentation has been pitched. I was pitching this at sort of ag professionals who have some basic understanding of the area. I wanted to highlight what are the factors that influence nitrate and nitrate loss to water. And that's primarily soil type and meteorology, and then the land use and farming practices as well. On the 26th of June, David Wall is going to go through some of that practical advice around how can you tailor the balance between what a crop needs to grow and what could be potentially lost to the environment. And it's complicated, it's complex, and it does require timely advice, and it requires farmers to be aware of the situation on their farm. No farmer wants to spend money on fertilizer that goes down the drain and into a river. That's a waste of money. That's not what they want to do. Where there is uncertainty is how much does a crop require at a specific time and how much is in the soil. And if we can improve the answers to those two questions, you will have much better precision fertilizer advice to farmers in a timely way. So that's what we're aiming towards, and that's what all our research is working towards.
Your paper and the research is suggesting that, look, we have huge heterogeneity in soil type, weather conditions across the country. The day of giving generic advice and generic stocking rates, recommendations, what do you see happening over the next number of years in terms of policy or in terms of schemes, or what would you like to see?
Well, I suppose what we're trying to do in Teagasc, between ourselves in Johnstown Castle and our colleagues in Moore Park, through Nutrient Management Planning Online and Pasture Base Ireland, is to provide farmers with the decision supports for their specific farm of what to do, when to do it for their particular system. And all of our research is going into that, be it use of new sensors, new technologies, new ways of analyzing data. So that's what we're moving towards, a time period where you might imagine an automated fertilizer spreader. It might happen. We're talking about automated trucks in 20 years' time delivering things around the country. If we had an automated tractor that was hooked up to this system and had fertilizer on the back of it, it would drive past some fields and not go into them. And it would go into certain fields and target them with either fertilizer or with manure, or it might be modifying the plant species or the sward composition in a particular field. So we need to move from, as we said, applied 150 kilograms per hectare per year to apply 10 kilograms in February, 30 in March, etc., to this is what you require on that field at this particular moment in time based on the current grass growing conditions. So that's
how far away do you think we are, Karl, from having a situation where farmers themselves could have these sensors in their fields for detecting nitrate losses? We know that there's a lot of work going into these remote sensors that are have battery life for 3 years and can be linked into the internet.
Yeah, so again, the part of Vista Milk is starting to look at that, particularly around improving the precision around grass growth predictions. Better, we don't even need to be able to sense, and there are sensors for nitrate and there are sensors for water. If we can combine the two, you can have much more precise management recommendations for both leaching and greenhouse gas emissions and for crop growth. So as I said, the idea here is to make sure there's enough feed produced on a farm to feed the animals on that farm. There was a comment earlier about nitrogen use efficiency being 25%. We're not worse than any other country in the world. When we look at the Netherlands, there's figures often quoted of 37 or 40%. The only reason they are higher is they have externalized their feed production. So the feed is produced somewhere else, and they've often externalized their manure management. So the manure is spread somewhere else. So all the losses associated with producing the feed and managing the manure are not accounted for in their balance. And a recent paper we published this year, I suppose, modified the way of calculating nitrogen balances, and we're pretty much the same as most other countries. And when we look at the NFS, there's a large range of nitrogen use efficiencies within the NFS, from much higher to much lower. So there's obviously things that farmers are doing to improve that other farmers at the lower end can learn from and modify their practices. And the main one there is tailoring fertilizer.
Karl, time has caught up on us again, and I don't know where that hour went. Thank you so much for excellent presentation and answering some of those tricky questions coming through there. Some really excellent questions coming through from our viewers today. Pat, thanks for helping with the questions today, and of course your oversight of this program. And I want to also thank Andy Boland and Yvonne Maher in the background, our production team, who are helping make all of this happen. Of course, our partners who are supporting the series. Before we go, I just want to bring your attention to other webinars that Teagasc is running at the moment. There's a dairy webinar that goes out on Thursday mornings. There's a cattle and sheep one, and so you can find all of those on the Teagasc website. And there's a specific dairy research one that has just started this week, and that it goes out on Wednesdays, I think it is, Wednesday mornings at 9:30. So do check out those other webinars that are available on the Teagasc website. Next week, we'll be talking to Dr. Karen Daly from Teagasc in Johnstown Castle about phosphorus and its interactions with soil and water. So I hope you do join us next week for our webinar next week. So until then, have a nice weekend and stay safe, and we will talk to you again soon. Thank you. Bye-bye.
Thank you.
Bye.